All right, good morning. So today is going to be lecture number 12, which will be the last lecture on clustering. Next week onwards, we'll move on to neural networks. So next Monday is going to be a little bit of a recap of classification and some extensions to the artificial neural networks we had seen. But Wednesday onwards, we'll move on to, Wednesday will be about convolutional neural networks. So these are more different kind of extensions of neural networks. So we'll dig deeper into the concepts of deep learning from next week onwards. Before going through today's clustering, I think a couple of logistical things. One, homework 4 was released yesterday. So today is the submission deadline for homework number 3 for distance learning students. And yesterday, homework number 4 was released. For in-person students, it's going to be due on Saturday, I believe, next Saturday. And for distance learning students, it's going to be on Monday. What else? So exam number 1, I think I released both the solutions as well as the questions, the ones that you had answered. If you have any questions, please let us know, either me or the TA. So again, we're not there to get you. So if you feel like there is something that you should have gotten that you did not, we went through many of them and gave additional points. For instance, I think a lot of you have written for that A divided by B and A by B and C by D question. You had a lot of, some of you had written 4, 2, 1 point something. I did go through and try to correct a few of them, but if I'd missed any, just come by. If you have gotten one of them correctly, then I'll be more than happy to add 2 points. Again, Canvas has the weird quirk where we need to put in exact numbers for it to work. Even 2 is different from 2.0, is different from 2.00, and so on. But yeah, those are the logistical things. So, coming back to the lecture stuff, yes. Yes. March 3rd is a Sunday. I think it should be on a Saturday. So I'll recheck that. But if it is on a Sunday, then I'll just make it it's Sunday. It'll be fine. But currently, I think the idea was to have it on Saturday, 1 day later than usual. Yes. Sorry? Yes. Yes, so this is the homework covers exclusively clustering about k-means clustering, GMMs, and some performance metrics, all of which we are going to be covering today. We have already covered k-means, and now it's going to be GMMs and some of the performance metrics. So yes, homework number 4 will be covered by end of today. All right, I think that's a good introduction into what we would be covering today, which is about the common clustering metrics. The Gaussian mixture models is something that we are going to be looking at today. So let's directly jump into GMMs by looking at what the deficiencies of k-means clustering are, and then thinking about, okay, what extra we can do on top of it. So look at the data set that we have here on the left-hand side. This particular data set, let's say you're not given any classes, you're not given any clusters, and just given this data set, you're asked to cluster based on 3, k is equal to 3. If you're using k-means, then the output would look something like this. And from a k-means perspective, this would make sense, right? If you're told that you need to have 3 clusters, maybe the first, there's one centroid somewhere here, another centroid somewhere here, another centroid somewhere here, and all these centroids are giving you a good, from a Euclidean distance point of view, this is a nice set of clusters. This is what you want from your clustering algorithm. But just look back on the kind of data that we have. If we start with the assumption that all data is random, that there is no reason why this data exists, then yes, any kind of clustering will do. But we know that we have generated this data, and most data is that way. You cannot simply have features that are independent of each other. They coexist together. So there's a specific data generation process, and we need to take that into consideration. And that is our desired cluster should look something like this, where this here is one cluster, this is another cluster, and finally this is the last cluster you have here. So in these cases, this is very similar to on Monday when we discussed the difference between Euclidean distance and something like a Mahalanobis distance, where the goal is we need to take the data generation process into consideration when we do the clustering part. If we take that into consideration, then our desired clustering would be something like this, where this orange, even though your cluster center is here for the blue cluster, and this orange part is much nearer this compared to something like this, which is the cluster center for your orange ones. It's, you can see that this orange portion here is much further away from its cluster, its cluster centroid compared to the blue cluster centroid, but still, geometrically, from a distance, Euclidean distance point of view, that is true, but from a data generation process, that is not true. So we want these characteristics imbued within our clustering algorithm, and to do that, we have something called Gaussian mixture models, so commonly called GMMs. So they're a probabilistic model for representing several normally distributed data within an overall data distribution. So there's a couple of very important things here. Let's start with the normally distributed one. So I mentioned before that there is a data generation process, that this is not random. We are assuming that there is a data generation process, and we are assuming that that generation process is normally distributed. This is, again, the simplest assumption we can make in terms of what a distribution could be. A normal distribution is the most simplest assumption, and we can use that and say that, okay, maybe my data generation process was normally distributed, so I need my clusters to also be normally distributed. So essentially, that is what this normal distribution is telling you. The next important point here in this sentence is the probabilistic point of view. So what do we mean by a probabilistic model? K-means assumes hard clustering. In other words, every single data point that we have here belongs to a single cluster. There's no ambiguity in what this particular data point, in which cluster it belongs to. But if you remember from Monday, we discussed two kinds of clustering. One is hard clustering, the other one was soft clustering. Hard clustering is the K-means clustering part, where there is no ambiguity cluster it belongs to. But then there might be a different kind of a soft clustering that there is a probability associated with it. Maybe this data point here belongs to this cluster with a probability of, 0.7. It belongs to the blue cluster with probability 0.25, and it belongs to the green cluster with probability of 0.05. This is essentially what soft clustering means. Instead of saying that it belongs to a particular cluster, we are giving a probability in terms of saying that maybe there's a cluster membership function that is involved, where you'll have a small amount of probability for one cluster, another probability for second cluster, and so on. So having just that motivation and that idea is where the probabilistic part comes into the picture, and that is the whole point of something like a soft clustering algorithm. So the first few slides are very math heavy, but this is something that hopefully you have seen before, like in I believe lecture 3, when we looked at naive Bayes algorithm and naive Bayes algorithm. And everything that we discussed then is going to be something that we are going to be discussing now, except there's going to be a small variation. Before, we always looked at a Gaussian distribution as e to the power of x minus mu square by sigma square, right? So this is for a single dimension, for single feature. If we want to move to a multinomial distribution, then your Gaussian distribution is going to look something like this, where it's x minus mu. Mu is still your mean, transpose sigma j. So your sigma square that we had here, which is your variance in a single dimension, becomes covariance in multiple dimensions. In other words, you probably have seen normal distribution something like this. This is a single x-axis. So just based on one x-axis, you have a normal distribution. But then you can have multiple other distributions as well. In 2 dimensions, this is what your Gaussians are going to look like. And the mathematical representation of these kind of Gaussians is based on this formula you have here. For a 2-dimension, of course, your sigma is a 2 cross 2 matrix. But if you have 3 dimensions, let's say it's going to be a 3 cross 3 matrix, and so on. And each element within it is how every dimension varies with the other dimension. The shape of the Gaussian that you see over here, like for instance, if I have a Gaussian distribution like this, again, this is a single distribution. If in 2 dimension, I could have a Gaussian distribution something like this, let's say. And if you see these level plots, it's essentially what we had discussed before. There's more concentration here, versus here I would say something like 95% of my data that is generated will be within this level plot, within this level curve. That is essentially, whenever you see these kind of plots, 2 or 3 plots together, that is essentially what it's telling you. It's just a level set, contour maps that is showing you where you can expect your data to be generated in. So if this is the case, if your Gaussian is looking something like this, your output, your covariance is going to be something like A, B, 0, 0. In this case, actually, since it's an exact circle, it's going to be A, 0, 0, A. So let me... Okay. So it's going to be A, 0, 0, A. This is how it is going to look like. But let's say you don't have this. You have a different number here. Your output is not going to be looking something. So if you want to, let's say, have a wider region here, then these two will remain 0, but your first and third element is going to change based on the amount of width that you're looking for. So this is the kind of, and if I want something like this, then that means that these will no longer remain 0. These will become something else. So this is how you control the shape of your Gaussian distribution. Again, from exam 2 point of view, these are the kind of questions that you can expect. Like we had generalized sigmoid function back then. Now we'll have these kind of questions, like given these Gaussian models, just predict what these values can be. Given A, B, C, D, what these values could be, or a 3x3 matrix, 3-dimensional graph, what these values could be. So just trying to understand and getting an idea of how these Gaussian distributions, these Gaussians look like, is going to be very, very essential. The idea of Gaussian mixture models is that there's not just a single Gaussian that is going to help you model your data, but there may be multiple Gaussians. And this is essentially what this image here is showing you. Let's say I have a data generation data process which looks something like this. It's like there's dots everywhere here. If I want to model this data using 3 different Gaussians, then maybe this is the output that I'm looking for. There's 3 Gaussians, one with, I think this is showing like whatever this mu value is. Let's say this is 0.25 and this is 0.4. So you have one Gaussian distribution with a mean at 0.25 in the x-axis in one dimension and 0.4 in the other. There is another Gaussian at, let's say, 0.5 and 0.5. And then there's a last Gaussian at something like, let's say this is 0.8 and 0.6. So these 3 Gaussians together is going to model my data. And that is what I'm going to use in order to cluster my data. So this is basically just a top-down view of, this one here, the one I just put a tick mark on, is just a side-angle view of the Gaussians. And the bottom 3 graphs are essentially just, the last one is more of a topographical map, but the bottom one is more of a top-down view on what these images might look like. Yes?
The matrix that you just draw, where does that come in?
That is sigma. So the way you control the shape of your Gaussian is by your covariance matrix. Variance gives you across one dimension. So if I want to vary the width or the length, let's say, across a single dimension, then I use these values here. If I want to change the skew of the matrix, skew of the Gaussian itself, I use the off-diagonal elements. Again, a simple Gaussian in 2 distribution looks something like this. So if I want to convert this here, then I need to change its mean, which is your mu. Here, your mu is going to be 0. But in this case, your mu is going to be something like 0.5, 0.5. And the shape itself of the Gaussian is given by your covariance matrix. So, based on knowing what your Gaussian is going to look like, this is the mathematical expression. There's a couple different things here. First off, the notation for pi. In this case, it's not 3.14. This is a very common notation that we are going to be using for prior. So back in naive Bayes, we had the idea of a prior. Without knowing anything about the data, I can assume that a particular sample belongs to all possible classes, right? So if there are 3 classes, then my prior was 1 by 3. which is exactly what pi j is going to stand for here. It's the prior, but the reason it's not called the prior in this case, or sometimes it is, but it's not the same notation, is that we need to update it similar to k-means, and that's why we're going to be calling it a pi at this point of time. And there are other, it's also sometimes called the coefficient of membership, but again, there's multiple. If you go through multiple online resources, it is going to say different values, different notations for this. But essentially, you should think of it pi as the prior. So given that, and given some kind of a q of x, which is my probability density function, GMMs, the main assumption in GMMs that any data generation process can be represented as a superposition, a linear superposition of these Gaussian distributions. That is, if I just take 3 different Gaussian distributions and add them together, that should be sufficient in order to model my data. Now, the number 3 is arbitrary, it's a hyperparameter, but at this point, if I know the number 3, if I know what k value is going to be, I'll be able to tell you that by generating a set of k Gaussian distributions, I can just simply add them. That's it, just add them together, and I can get my data, I can model my data essentially. So it's just a linear superposition of multivariate Gaussian distributions. Hence, you have the sigma. If I have k Gaussian distribution, k equals 1, j equals 1 to k, pi of j, which is your prior, multiplied by q. In other words, any single element x will have a certain prior associated with it. That means that it could belong to, if I go back here, somewhere I've written, yes. So this particular element has a, let's call it pi 1 of 0.7, pi 2 of 0.25, and pi 3 of 0.05. So these are the priors that are associated for every single data point, its membership towards a particular cluster, and that, when it's linearly superposed against its corresponding Gaussian distribution, just a simple addition should give you back the data. This is the major assumption that we are making within GMMs, or Gaussian mixture models. Any question about the motivation, about what we are discussing here? All right, so assume that the cluster to which xi belongs to is labeled as zi. This is another notation. We'll generally be using this across neural networks and any generative modeling. We assume that there is a certain variable that we don't have access to that we'll not be able to change. Like I can go to xi and say that I can add noise, xi plus 0.1, xi plus 0.2. But we are assuming that in a generative modeling process, your method itself, algorithm itself, has some kind of a latent distribution associated with it that is given by zi, and we have no control over that zi. Our algorithm will be able to take our data and construct this model and give an output, which is going to be zi, but we ourselves cannot go in and change this kind of a zi. That's why it's called something called a latent variable or an unobserved variable. And the prior of zi is denoted by p of zi equals j is equal to pi of j, essentially. So it's the prior. This is why I wasn't using, we are not using the same exact terminology that we were using before. It's just that it's a prior of your latent variable than your exact variable that is going to exist. In the beginning, it is going to be the same, but then we are going to do something called expectation maximization algorithm. You'll see then that, okay, your posterior starts becoming the prior in that particular case. So there's a small change in your notations at that time. So whenever we say theta in GMMs, we are referring to 3 different variables: the mean, the sigma, which is a covariance matrix, and the pi, which is, let's call it the prior or coefficient in this particular case. The posterior itself, there's, again, if you look at different online resources and papers, you'll find different notations, different terminologies for it. Posterior is sometimes called the responsibility as well, which is essentially, again, your class membership, how likely it is that a particular data point belongs to either cluster 1, cluster 2, or cluster number 3. Getting the posterior is exactly similar to what we saw in naive Bayes, which is we're just using a Bayes rule in this case. The numerator, denominator, everything is exactly the same in order to get our posterior. Now, GMM is a generative model which specifically models this P of Zj and P of Xi given Zj. We'll talk more about what this exact word means when we discuss neural networks. It's a little bit more clearer over there. We have a specific encoder, and we'll get a latent representation over there. So it's much easier to understand this point of view. But just remember that GMMs are generative models that can generate new data since they have already modeled the underlying distribution of the data. Also, GMM is a soft clustering method. As we mentioned before, every data point has a coefficient of these membership classes. So, 0.8, 0.15, 0.05, these are all memberships towards certain clusters. The parameters are comprised of three things: mu, sigma, and pi. We discussed this already. So the way we can, let's say I have a trained GMM model. The way I can now say that a particular data point belongs to this cluster, cluster number 1 or cluster number 2, is by using something called maximum likelihood estimation. This is something that we had seen as well. In fact, I don't think we had mentioned this in the lecture itself, but in homework number 2, it's the only way you can, after getting naive Bayes, you need to get your reference. So that is the only way. So the words maximum likelihood estimate was only used in your homework, but I don't believe I had put it in any of the slides. Now we are going to look at what exactly it means. So maximum likelihood estimate, as the words suggest, we are looking at the most likely estimate for a given data point. It could belong to cluster 1, 2, or 3, but we are looking at the one that is the most, the maximal likelihood that it belongs to a particular cluster. The way we do it is very simple. We start off by making the same naive Bayes assumption that we had before, which is that it is independent in terms of cluster membership. It could belong to cluster 3 or cluster 1, or it could belong to cluster 3 and cluster 2, and all of them are equally likely. It's not like each of the clusters is dependent on the other clusters, which may not be true, right? So if I go back to this here, a particular data point here can belong it's equally likely that it belongs to, let's say, the orange cluster or blue cluster, but it's unlikely that it belongs to the green cluster. But still, we start off with the assumption that all these things are equally likely, that all classes or clusters are independent of each other. And we get this very simple framework, which is pi. The sigma pi n is something that we had seen before. This is from the previous slide here. Was it here? Yes. Yes, here. Your Q of x, which is your data modeling itself, is dependent on your prior and your normal distribution model. So now we are saying that this is for a single distribution, by the way. Given a single k is equal to 1, this would be your mathematical formulation. But if there's more number of k's, then we have I is equal to 1 to capital N, which in this case, your data set, you're looking at every single data point being identically distributed with each other. You have j equals 1 to capital, the small k over here, which is essentially you're multiplying across different k values. Adding across different k values. This is again based on the linear superposition principle. Where was that? Yeah, linear superposition principle, which we have over here. Of course, so the only difference here is that we are doing it across different data points, which is 1 to capital N. Now, log likelihood, we usually want to take it because, again, as you saw back in homework number 2, we don't like dealing with the idea of multiplication across different, if capital N is like 10,000 million, it's very, very hard to deal with these multiplicants. So instead, we just take a log function. And the reason log works is because it's monotonic. So it doesn't matter if you minimize the expression 1 here, or if you minimize expression 2, the output you're going to get is going to be correlated with each other because it's just monotonic. There's no increase, decrease, valley that exists within the log function. So it's just a simpler in terms of mathematical representation. So once you have the log function, we do exactly what we had done before. We have a normal distribution. The only difference, of course, is that from before, now we have k more than 1. Before, we just had this very simple expression that we could solve for mu and covariance matrix, right? I believe it was one of the questions where we had asked you to take, 15 or 17 different samples and literally find what the mu and sigma values are going to be by adding up everything and taking an average. It was very straightforward in order to do it there. But now, we'll have more than one cluster. K is not equal to 1, it'll be more than 1. So we cannot use these kind of closed form solutions in order to estimate our mean and sigma values. Because again, we have a different parameter called pi, which basically allows a single data point to be in multiple clusters. So back in homework number 2, your question read something like, for class 1, find us the mu and sigma. For class 2, find us the mu and sigma, right? But in this case, each data point does not have a class associated with it. It has a pi associated with it. So it becomes infinitely more complicated. Well, infinite is the wrong term, but it becomes more complicated in terms of trying to find your solutions in this particular case. You won't have those, you cannot have those kind of questions because there is no exact membership towards a particular class or a particular cluster. So you don't have a closed form solution in these particular cases. This is when we use something called expectation maximization algorithm. So MLE, which is the maximum likelihood, is for the inference framework. Once you have a good Gaussian distribution, then you can take the log likelihood. You can look at the class that has the highest likelihood and infer that this belongs to that particular class. But if you don't have that Gaussian distribution itself, that is when you start using expectation maximization algorithm. In many ways, this is very similar to k-means clustering, and in many ways, it's similar to the training algorithm usually that we do. We are basically training our parameters theta, and in this case, theta, instead of being w and b, it's mu, sigma, and pi. These are the 3 things we are kind of training in order to get the best possible Gaussian mixture models. Any question regarding the difference between MLE and EM is very important. You can think of EM, an analogy for EM is going to be training, while MLE is more from a testing perspective. All right, so let's dig deeper into the idea of expectation maximization. So in k-means clustering, basically what we did was we had 2 stages. There was something called an assignment step and an update step. What we did in assignment step is, given n number of data points, we clustered them into separate. We randomly chose a particular centroid and said that these m data points belong to cluster number 1, these k data point belongs to cluster number 2, these l data points belong to cluster number 3. So that was the assignment part. And then we found the distance between each of these data points to the centroid, calculated a cost to it, and decided that maybe this is not the ideal cost. This is not the ideal way to design our clusters. Maybe this particular data point belongs to cluster number 2 rather than cluster number 1. And we updated it. We updated where our centroid is going to be and started reassigning everything. Right? That is exactly what we do in this case as well, except from now it's more of a probabilistic perspective rather than a deterministic perspective. So in this case, we iteratively estimate the mean of the Gaussian mu and the posterior gamma, and in turn estimate the posterior. So this is estimate the posterior. I think this should be gamma j. This is j. I think this should be t plus 1. So this should be t here, and this is t plus 1. So for a given mu j, there is a posterior that is given by mu j of t at, let's say, time t, and then our goal is to get gamma j of t plus 1, the posterior at the next step. So your mu j is very simple right now. Given in the beginning, it's just basically a set of all the mu of your data points. So given your gamma ij for a particular posterior, you're just taking the xi values and dividing by all the posterior values, similar to what we had done before. So mu j is the weighted average of all samples xi, weighted according to the posterior probability mu j. Again, this is exactly similar to what we had done before. Initially, we start off by doing this. So we initialize the mean mu j of 0, sigma j of 0, and coefficient pi j of 0, and we get gamma I. In the beginning, of course, it is going to be 0, and given this simple naive Bayes algorithm, we are estimating what the posterior is going to be. This is at t is equal to time step 1. We start off with simple initial random mean, let's say covariance, and some kind of a 1 by k as our prior. We just use a simple naive Bayes algorithm that we have already used in order to find what your posterior gamma is going to be. From the next step, we start changing this. So our gamma that we had before, think of this as now the prior for the next step. So you'll be using this within to calculate your mu framework. This is exactly, again, similar to what we did in k-means clustering. We started moving our centroid to a different location and using that as the new centroid. This is exactly what we are doing, except the centroids right now don't have an XY coordinate associated with them. They have like a mu and a sigma associated with them. So the previous cluster is now our prior, essentially. The previous posterior of our cluster is our prior in this next step. So that is how you would estimate the mu again. You would go back and you would re-estimate what the mu is going to be. You re-estimate what the sigma is going to be. You re-estimate what the pi is going to be. And now you do your maximum likelihood estimate to see what the output is going to be. So in a way, this is like your training epoch, and this is your validation. Right? At the end of every epoch, you do some kind of a testing to see what your output is going to be, which is exactly what you're doing. You're using the expectation inside the expectation maximization algorithm. You've completed one step. Now you're looking at what the maximum likelihood estimate is. Based on that maximum likelihood estimate, you're going to have a convergence criteria. We'll talk about what that convergence criteria is in a bit, but if that convergence criteria is satisfied, then that's it. You're done with your EM algorithm. You have the best possible clusters that is possible within the data. But if not, then you need to redo this over and over again, which is again very similar to what you did back in k-means. The only difference, of course, is this is a more probabilistic framework. So in this case, your convergence criteria that we'll be using is essentially that there's no change in your log likelihood. Your maximum log likelihood is going to remain the same, or it's going to be within a certain tolerance region, epsilon. Similar to what we did in gradient descent, we had a certain tolerance there. This is the same thing we'll have right now as well. You fix your tolerance. If it's something less than that, then you have your log likelihood that has, let's say, saturated. So there's no need to do further any kind of analysis. So we have a two-dimensional example here, which basically goes through the process. In k-means clustering, it was more easier to find these kind of examples to make it our own. In 2 or 3 iterations, we would see what the answer is going to be. But in GMM clustering, it is not like that. To get the final output, it's about 150 epochs for this simple data set to get these kind of clusters, but it gives you better clusters compared to k-means clustering. So in this case, we start off with some random iteration 0, with some random mu and sigma. So we are starting with this as our centroids, and our sigma as well. You can see that it's, it's not 1 if it were, it's not 1 and 1, it's basically 1 and 2. That means it's something like this oval over here. And same thing in this case as well. So we are starting with a different kind of a Gaussian distribution that is not simply just 1 and 1 in terms of its covariance matrix. Again, it could be something random, and we update this. In iteration 50, it's going to look something like this. Again, this is not easy to just show you in the slides. This is something that has to be coded, and you need to see it across 50 different iterations or 150 different iterations. So essentially, your homework is going to be covering this. The first question is more of a toy example to get you into just finding some kind of very simple solutions. But I believe like question 2, 3 onwards, you'll be dealing with these kind of data where you need to do multiple iterations in order to get to a certain stage. Again, the only difference between the idea of k-means and the idea of GMMs is the probabilistic point of view. If I were to have, instead of a 2-dimensional example, like a 1-dimensional example, let's say I wanted to cluster these things together, something like this. Your k-means clustering would start off with this, and basically suggest that, okay, this my nearest cluster, this belongs to this cluster, or this belongs to this X cluster over here. The differences in GMM, you're going to put these two things. The mean is going to be at the centroids, but you're going to have some kind of a variance and a covariance associated with it. That means this particular element will have, I don't know, like 0.7, 0.3 associated with it. So it's 70% likely that it belongs to the left-hand cluster, and 30% likely that it belongs to the right-hand cluster. So because we have this additional complication, there's a probability involved, and this probability is reflected in how we model this distribution. Instead of just doing x minus mu transpose x minus mu, which is basically what your k-means is doing in terms of the Euclidean distance. There's a sigma inverse between them as well, which is taking the data generation process and multiplying all this. There's a pi value, which is your 0.3 multiplied by 0.7. These are the only two differences that exist between a GMM module and a k-means, at least from a qualitative perspective. But of course, when you try to implement this, it's going to be a little bit more difficult in terms of just the coding part and the math part that is associated with it. Any question about GMMs? So next, there's something called a mean shift clustering algorithm. It's a little bit even more complicated than GMMs. The idea in mean shift, the problem with k-means clustering and GMMs is that you need access to the k value from beforehand, which is that you have, you don't have, you need to be given the number of clusters that you need to divide your data into. But mean shift algorithm is something that is going to remove the need for that parameter k and is going to find k by itself in order to find a solution. So I do have a few slides on this, but I did not go into the actual mathematical details of everything. I won't go through in the slides right now as well during the lecture, but if you're interested, then there's a lot of resources about mean shift algorithm that goes through and gives you a good idea about what they are. But with that, let's move on to the next part, which is about evaluating cluster performance. So this is how we usually end, like when we have classification, regression, this is what we did as well, right? We had these performance metrics, and the last portion of those topics was about the classification metrics. So same thing in clustering as well. So we finished talking about all the evaluation, all the clustering methods themselves. Now we need to discuss, okay, you have GMM versus k-means. How do you evaluate one versus the other? Which would you use given a data set and given some data points? So that is taken care of by something called the performance metrics in this case as well. So the difference between, let's say, classification and regression versus clustering is the idea of access to ground truths. We started off by saying that this is an unsupervised learning algorithm. That means that there are no ground truths available, which means that simple measures like accuracy, where we just had a prediction versus ground truth, and we just saw what the difference between them. Maybe those are not applicable in this case. There's no way we can say whether you have k-means is correct or GMMs are correct. It's that we sometimes, before when I said that GMMs are better than k-means, it's because I knew that the data generation process was a Gaussian. So I knew that some of the data, that the clusters should not look like the k-means. Rather, it should look like the GMMs. So there was an inherent ground truth within my thinking where I knew this kind of a generation process existed. But let's say you don't have access to any ground truth. So this is where the question then becomes, okay, how do you evaluate your clustering algorithm? And that makes it a little bit more difficult compared to something like classification and regression. We'll have two criterion that we will discuss in terms of evaluation performance, which is internal and external clustering algorithms, evaluation metrics. The internal evaluation essentially states that the clustering result is evaluated based on the data itself that was clustered. So this is more of from the perspective of unsupervised algorithms. So this is not telling you that you need access to ground truths at all. Without given access to ground truths, you will be able to use these kind of internal evaluation metrics to decide if one is better than the other, if any of the clustering algorithms is better than the other. So these methods usually assign the best score to the algorithm that produces clusters with high similarity within a class and between classes. Right? So this is essentially what we want. We want each cluster. Let's say we have ideal data that is something like this, and another data point set of data that is like this. This is very simple, right? This is one cluster, this is another cluster. We want to make sure that this particular part is not clustered with the left-hand cluster, let's say. So we want to make sure that the distance between these centroids is very high. So let's say this was not the case. This was incorrectly clustered in a different one. Then your centroid would be somewhere here. So the distance between these two centroids is not that great right now compared to something like this. So this is the main motivation behind. Just the way your cluster centroids are assigned will help you, will tell you how your cluster is, essentially, how your clustering algorithm has done. And that essentially is what your internal evaluation metric is helping you with. So one thing you'll notice is that these metrics are biased towards algorithms that use a same cluster model. So right now I just use the word distance, right? So distance is something that we use constantly in both the algorithms, but or maybe I should say proximity measure is something that we use in both k-means and in GMMs. But in k-means, what we used was more of a Euclidean distance versus now we were using more of a Mahalanobis distance. So if the model that I'm using to evaluate this distance is based on Mahalanobis, then maybe that is going to improve GMMs. But if it's based on Euclidean distance, as it usually is, then we are looking at more biasing towards the k-means clustering algorithms. We look at three things here: the Davis-Bolden, the Dunn, and the silhouette coefficient. External are kind of the opposite. We start off the algorithm with the assumption that it's unsupervised, so we don't have access to ground truth. But maybe we have access to a small amount of ground truth, and that is something that we can use in order to evaluate the performance. And this is quite common to do as well. You know, if you have millions of data points, it's not possible to label all these million data points and train everything. Rather, what you can do is label about 10,000 of these data points and use those 10,000 for testing. You can use the remaining, 990,000 data points to do all your clustering algorithm, and the remaining 10,000 you just evaluate how your algorithm has worked. So based on that assumption that you have access to a small amount of ground truth, you have something called external evaluation techniques, and this is evaluated based on data that was not used for clustering, such as known classes and external benchmarks. So external benchmarks, again, will have their own ground truths, but essentially you have access to these class labels during your evaluation framework. That is what is the difference between your external and internal clustering algorithms. So we have multiple algorithms, evaluation metrics. We'll be looking just at a few of them. We'll look at the purity and RAND index. I think we have a slide on mutual information as well. F measure, it's a variation on the F1 score that we had seen before, also exists. Jacquard and Dice index are not something that we're going to be looking at, but these are more advanced metrics in terms of trying to find your performance. So let's start with the internal clustering metrics. The first one is the Davis-Bolden index, a very intuitive metric in terms of what I need out of my clustering algorithms. Firstly, let's look at the denominator, which is called the inter-cluster distance. I want to make sure that the distance between my clusters is very high. That is, if I have some data like this, I want to make sure that there's nothing incorrectly clustered here, right? If it is incorrectly clustered, then this cluster is going to look something like this, which I don't want. I want these kind of round clusters that exist. So the distance between the, let's say, the centroid of each clusters is something called the inter-cluster distance, and we want to maximize that as much as possible, which is essentially what we are trying to do here. Your denominator is the distance between the MR and MS, where MR is the centroid of cluster R, and MS is the centroid of cluster S. I guess that's, yeah, DMR-MS is the distance between centroids MR and MS. We want to make sure that this is maximum in the denominator. The numerator is something called intra-cluster distance. In other words, if I go back to this figure I had, let's say I have this as my cluster here. The intra-cluster distance refers to the distance between every single data point and the cluster. And we want to make sure we maximize this distance. So what does that mean? We want to make sure that the kind of cluster that we have generated, if this is my cluster, all of them are as far away from each other as possible. This is not looking at the each other part, but it's basically saying that it's as far away from the center as possible. So this is as opposed to another clustering algorithm that has clustered all these things like this. And then there's one here, one here, one here, and one here, right? So ideally, we don't want this as our cluster. We want this as our cluster. The intra-class distance, so between the centroid and all data points, ideally must be high within the same class, but then it has to be much larger against some other class. So let's say there's another class cluster here versus another cluster here. This is the inter-cluster, I-N-T-E-R, inter-cluster, and between this is the intra-cluster. So any algorithm, yes, question? Yeah, I mean, this doesn't make as much sense when all data is easily separable, but when it's not separable, if I show you in something like this, where was that? Yeah, if it's something like this, then look at these kind of clusters here, right? So let's discuss between k-means and GMMs. So in this case, let me start off by just removing all this first. Yeah, so in this case, this is the centroid. I'm just looking at two clusters here, the blue cluster and the orange cluster. The inter-cluster distance is very high. So this is based on that one index, the Davies-Bouldin index. This is very good. And the intra-cluster as well, I mean, it doesn't look high, but compared to the next one we'll show, it is much higher. Right? So there is some kind of an intra-cluster distance. Look at all these. This is extremely high, which is kind of what you want. And the inter-cluster distance is very high as well. But if you look at GMM, the inter-cluster distance is going to be lower compared to the previous one. So it's somewhere here and here. So this is the intercluster distance here, while here it was somewhere here and here. Intercluster is going to be more. But your intra-cluster distance in this case is going to be different than what it was. Now, I'm using the word distance very lightly here because in this case, when we discussed the distance, it was Mahalanobis distance. But right now, when I talk about every distance, it's simple Euclidean distance. That is the D metric I'm talking about right now. The intra-cluster distance is much higher in this particular case. So this gives you like a trade-off between intra-class versus inter-cluster difference. Yes, when the simple examples that I'm showing here that I just drew, it doesn't make too much sense because everything is separable, but when it's not, these kind of indices make more sense in those cases. So that is what the intercluster and intra-cluster distance mean. Very simple, just take the distance between the clusters, the centroids, and between every single data point and the centroid itself. Now the distance could be anything such as L1, L2, Minkowski distance. You can also use some kind of Mahalanobis distance. Generally, when we say these indices, we are looking at the L2 distance, but of course, it depends on the data generation process and what kind of application you are using it. We want a smaller dB index. We want to make sure that the intercluster distance is very, very high. This is essentially what we want. Intra-cluster distance, this is not something you can always, let's say, have control over. But ideally, if it's lower, then it's better as well compared to something like that. Basically means that you shouldn't have clusters that look like this and then something far away here, right? Because this is going to increase the value of your intra-cluster distance too much. But of course, again, it depends on the kind of distance you're using, and you'll always not have control over what the intra-cluster distance is going to be. If you read more papers, you'll see that there's other ways that intra-cluster distance, you'll have something called uniformity, density. There are other ways of characterizing what the intra-cluster distance is going to be, but it's beyond the scope of this class. Just think of it as anything within the cluster is intra, and between clusters is inter-cluster distance. So next is a done index. It's very similar to, actually I think I did not mention one thing. Yes, there's a max function here. So let's say we have 5 different clusters. You're taking a single cluster for r equals 1, and you're looking at how far it is, the inter-cluster distance across all 5 clusters, and you'll have a certain number. And if it's 5 different classes, you can have 5 different numbers in this case. And you'll be taking the maximum of these values as your index. Now, what done index does is it does that a little bit differently, where it tries to minimize. So here you take this together and find the max, while in the done index it's done separately, your numerator and denominator, which again is the same thing as it was before, but it's done separately. You're not taking the division, the quotient together and looking at the max, but rather you're minimizing the numerator separately, you're maximizing the denominator separately, and you're finding your done index. Other parts are the same. So you have d of mr over comma ms, which is the distance between 2 clusters, and it could be some distance between centroids, which is essentially your, another difference here is that the numerator from before is the denominator, and denominator before is the numerator. So if you saw here, it's d of mr comma ms, so that is the numerator in this case, while the denominator is the opposite. Right? So there's 2 differences. It's separately minimizing and maximizing, and what numerator was and denominator was is different. So because you have interchanged your numerator and denominator, instead of having a low index as you had before, now you want a high done index. You want to make sure the intercluster distance again is maximum, so you want your numerator to be very high, which makes sure that you need a high done index is more desirable. So d of z, which is the denominator here, it may be measured in a different way, such as the maximal distance between any pair of points. Again, this is completely dependent on you, how you're trying to find these distances. Right? Before we just talked about average distance here, but maybe it's not an average distance in done index. You can have a maximal distance. In other words, if given these points in a cluster, instead of calculating distance as an average, I'm just going to take the most difficult 2 points, let's say here, and by difficult I mean the furthest points from each other, and I'm going to calculate this distance and say that this is d of z. Again, if you're asked what done index is, you'll also be, this is the default you can take. Otherwise, you'll be given what kind of distances you need to use in order to calculate these values. If it's max distance, you should remember L0 norm, L infinity norm, those are the things that we are looking for essentially. The last algorithm is, or the last performance metric is the silhouette index. So this, again, we don't have access to any ground truth, right? That is the same before, that is the same right now as well. In other words, we just have the output of our clustering algorithm. So in this case, let's say that we have 3 different clusters. We'll take a particular point x, and we are just going to calculate the silhouette of this particular clusters of x's cluster and the silhouette of all other clusters. And by silhouette, I basically mean this thing here. And we are going to use that in order to create an index that is going to be called as the silhouette index. So it basically is the algorithm itself is basically very similar to k-means, except there's no difference in terms of assignment and update. So given an algorithm's output in the clustering, we are basically assigning different values to a particular silhouette and then taking the distance between our region of interest silhouette, which is the x silhouette, which is the blue in this case, and all other silhouettes in order to find our index for this case. Of course, the problem then is that it's going to always favor k-means. It doesn't matter what you're doing, what better algorithm you're using in terms of clustering, but it's always going to favor k-means. It's going to give you is very biased towards those kind of algorithms. So the way it works, again, the difference from before was that we had a biased estimator before. In other words, whenever I was taking average here, it was either across k, or this distance was an average distance that we were taking, right? So that means we were taking, let's say, 1 by n, or if we had about L elements within a particular cluster, we used to take 1 by L. Here we are using an unbiased estimator, which means that we are removing x from our data clustering. That means we are just going to be taking 1 less. Otherwise, it's still the same as the distances that we were using before. So it's just a distance. We are constructing that kind of a table that we did on Monday of between xi and xj. But the difference, of course, is it's an unbiased estimator in this case. D is a distance measure, and mod CR is the number of samples in CR. When I said L, which is 1 by L, which is basically mod of CR, which is the number of elements in that's associated with the centroid CR. So we have AI that is based on this. Next is calculate the average external dissimilarity of point xi to samples in other clusters as the smallest average of the distance from xi to all samples in each other cluster. So based on this element that we are taking, x, we are now going to calculate the average across all different clusters that is going to exist. Before, in the Dunn index and the Davis boulder, we were just looking at the centroid, right, which was the center point, your MR and MS, which is not the case right now. We are taking across all data points that does not belong to this particular cluster based on the algorithm that you are looking at. So based on that, you can define a coefficient which is going to go from -1 to 1. This coefficient is 1 minus AI by BI, 0 BI by AI minus 1. So again, AI is something that exists as an within your own cluster. So think of it as an intra-cluster distance versus BI is the inter-cluster. So it's between the clusters. Except you're not just doing it against your mean, your centroid in this case. You're doing it across every single data point. In other words, you need to create a table. Let's say you have 5 data points. So cluster 1 has 2 data points, and cluster 2 has 3 data points. What you need to do is have a 2 by 2 matrix to calculate A. So in this case, you need to have that 2 by 2 matrix, and you're going to take the average across everything. Right? So to get that A, you need to do that. Then to get B, you need to get a 2 by 3 matrix. I hope that's clear why. So this is x1, this is x2, and this is, let's call it x21, x22, and x23. So across all the elements in the different cluster, you need to find your distance between x1 and x2. And the smallest average distance from xi to all samples within a particular cluster is something that you're going to take and use that as your silhouette. Again, the difference from before, instead of doing for MS, you're doing for the silhouette. In other words, across all data points within the cluster. One good thing about this algorithm is that it's something that you can use to verify whether K is correct or incorrect. So it goes from 1 to -1. If you order all your X data points, let's say I have about 1,000 data points, and I'm going to order those data points in terms of the highest value of your silhouette, you see this kind of output, which is based on the fact that you have 3 different clusters. You'll see that after a certain time, your second cluster comes into existence, which is, let's say this had about 700, or I had started with 1,000, right? So let's say this had about 300 data points, 400, and 300 again. So if you take for cluster number 1 and plot all the silhouettes, you'll notice that it goes down towards 0. That means that these points are closest towards, let's say, something. So with 0, then that means that they're almost inseparable or almost overlapping, which tells you where your result is going to be. If your value is less than 0, that means there is some kind of an overlap within your framework. So your what has happened now is your BI by AI is in fact -1. So it's less than 1, or your silhouette is less than 1 in this case, which tells you that there is some kind of an overlap within your framework. So maybe that would tell you that either your clustering algorithm is incorrect, or maybe you would have needed a different amount of K, that you need to increase your K. So if I look at the GMM results here at the bottom, I may conclude that this is incorrect, that I need a different K value, that I need to increase my K value, because look at how much of my K value is incorrect in this case. So this might be a way for you to choose your K value. So that's why silhouette index is a good way to try to analyze the value of K that you have chosen. So those are internal clustering metrics. Next is the external clustering metrics, which is we are now assuming the existence of ground truth. So if we have an existence of ground truth, now we can go back and say TP, TN, FP, and FN, right? So these are the 4 metrics that we'll be using in order to calculate something called a RAND index, which is an external clustering metric. So let's start off with these assumptions here, that given n data points, x1 to xn, we have 2 clustering of x. One is ground truth clustering. Again, we're assuming that we have small access to a small amount of ground truth. And then there is a computed clustering. This could be from k-means, or it could be from GMM, or any other clustering algorithm. So we have 2 clusters, or I shouldn't say that. We have 2 ways of clustering, either via Q, or which is our algorithm, or via R, which is our ground truth. Now we measure the number of pairs where co-occurring elements in the same pair. So in this case, let's say same class both in R and Q. This A over here, both of these elements are within the same cluster if I use Q or if I use R, right? That exists, that is true. So think of this as true positives. Then let's look at the last one. So different classes both in R and Q. So the last one is D. So if you look at D, this is also correct, right? In this case, both of these elements, this circle here and this triangle, are correctly classified or are correctly within their clusters in both Q and R. So you think of this as true negatives. They both are there in their respective clusters. Doesn't matter if it's on R or if it's in Q. The middle portion, depending on which R and Q is going to be, can be true negative or false positives and true negatives. So let's look at the second one here. The same class in R but different in Q. B. Let's look at R first. So the circle and triangle are in the same cluster, right? Which is the opposite case, which is not true in Q. So these don't match together. That belongs in the second category here. The different classes in R but same in Q, right? Which in this case is C. So these 2 things are in different classes in R, but when you look at Q clustering, it is the same thing. So these are 4 different indices, which you can think of again as TP, TN, FP, FN. Once you have access to them, your RAND index is same as what you would get from an accuracy perspective. It's the fact that your A's are clustered correctly, your D's are clustered correctly. It's in separate clusters, but they're in what cluster? Both the clusters are matching together. So those are the numerator, and all the other ones, A plus B plus C plus D, is going to be your denominator. Now we don't call this accuracy because it's a little bit it's a little bit more complicated. We are just using A here, right? But these 2 are correct as well. So these 2 are correct as well. These 2 are correct as well. So it's not, we need to measure all of them. So all these co-occurring data points have to be considered when we talk about A, about D, B, C, and D as well. So just to give you an idea of the complexity. So in this case, this particular slide, it's the same as your confusion matrix. If you have a binary classifier and you're looking at a confusion matrix, it's very, very similar to what we have shown in this case. Everything is, same cluster in R, different clusters in R, same cluster in Q, different cluster in Q. You can basically count, do the exact same thing that we did for classification. But this is not always, if you remember classification, the reason we went towards true positive, true negative stuff away from the accuracy was that accuracy is problematic when there is imbalanced data. The same thing exists in this case as well. Let's say cluster 1 had 10,000 data points, and this cluster had only like 5 data points. So your RAND index is going to overestimate your result by quite a bit when it comes to finding the result in this case. So what we have is something called an adjusted RAND index. This is like the formula for this. Now I'll motivate how you get this, but again, it's n choose 2 in order to get these results. So let's go back to RAND index. Instead of thinking about it as just A, B, C, D, let's think about what it represents. So for instance, I have 3 different clusters here in clustering algorithm R and clustering algorithm Q. If I want to calculate all possible A's, right, the way I would do it is by choosing nij2, where ij is r and q over here. So in other words, so let's start by looking at these 4 values here. In both cases, the 4 values they exist, right, in the appropriate clusters. So that means that I can choose, let me use different colors for this. I can choose these 2, and they'll be A's, because they're A's here as well. Now I can choose these 2, they will be A's. I can choose these 2, and they're going to be A's. So there's 3 different ways for me to choose A from these 4 things, right? In the same way, I can choose this, and so that's 5 right now, 3 plus 2. And finally, I can choose this and this, right? So there are 6 ways for me to choose these values, which comes down to 4 choose 2. Again, these are co-occurring data elements, co-occurring x's. So I'm choosing 4 choose 2 in order to find all my A values. Let's look at this, and again, this is correct, right? That's why I'm using 4 choose 2 in this particular case. Now let's look at these 2. These 2 are also correct. They're within the same cluster. R says it's in the same cluster. Q also says it's in the same cluster. So basically, this goes down to choose 2 choose 2, right? So there's no other way of choosing 2 elements. So it's just 2C2. So 2C2 plus 4C2, 1 plus 6 gives me 7. So the value of A is going to be 7 in this case. When we looked at this before, it was more from just a conceptual point of view. But when you actually want to calculate what your results are going to be, then this is the formula that we need to use. So your A values, you're looking at all the elements which are correctly classified in particular clusters, and then using that in order to calculate the something choose 2. And that something is dependent on the number of elements that exist. Same thing with B as well. Let's go back and see what B is. So B is pairs that are united in R but separated in Q, right? And how do we do it? An easy way to do it would be to look at everything that exists within R and just subtracting with what it intersected with in A. For instance, in this case, NC2 would be in R, there are 3 different clusters. There is 2C2 here, there is 4C2, and there is another 4C2, which is essentially what you have. All the clusters that can exist within R is given by this in this box, and you just subtract it against the ones that you already have, which is A, and A is given by pairs that are united both in R and Q. Right? You're looking for the ones that are united in R but separated in Q. So find everything that are united in R, and then subtract it with those that are united in both R and Q. So that gives you, think of it as set theory. You're just subtracting those regions that have been removed that are united in both R and Q. And once you do that, you get this particular formula. 2C2, 4C2, 4C2 minus 7. Same thing in the other case as well. C is basically the opposite. Now you'll be looking at Q. So let me, so here this is 3C2, 2C2, and 5C2. Which is essentially what you have here. You're looking at all the elements which are united in terms of clustering in Q, and then subtracting against the ones that are united in R as well, so that you'll be able to find the ones that are divided, that are separated in R. So you'll get those numbers. The last one, D, the true negatives, pairs that are separated both in Q and R. Basically find all the elements that may exist, like all different co-occurring indices, which is basically your, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 10C2 because you're looking at any possible elements that can exist or any possible combination that can exist and subtracting it against everything which are co-occurring together, which is A, B, and C in this case. You'll get certain result, and based on that, you'll be able to calculate your RAND index. This is almost impossible just to look through and get the, yes, question?
I'm confused how the matrices correspond to the numbers. Like 2 is equal to 1, but then 4, 2 is equal to 6.
I'm not sure which you're talking about.
Like for B equals 2, 2 plus 4, 2 plus 4, 2.
Yes, okay.
7. Why does 2 correspond to 1 and 4 correspond to 6?
So there's different ways. So this is basically 4C2. It's 4 into 3 divided by 2. So it's given by this formula here. So there's two ways of representing combinatorics. The way we speak, at least the way I speak, is like 2C2 but it can also be represented as 2, 2. So in this case, it's easier to, whenever we write it, it's easier to show it in terms of just a simple matrix, 2, 2, versus when we speak it, we usually say 2C2, which basically is 2 multiplied by 2, 2 multiplied by 1 divided by 2 in this case, which gives you 1. And 6 is 4C2, which is 4 multiplied by 3 by 2, which is 6. And you can use the same methodology for everything. Again, this is something that you would have to go back and look through the slides like 10 different times. It's pretty straightforward in terms of set theory. If you think of all your like each of this as its own set, then basically you're just subtracting all different sets from it. That's all you're doing. So once you have a handle on that, the way you get your rank index should be, or RAND index should be straightforward. Now, we won't go or discuss too much about the next set of formula, but the calculation is the same. So whenever we have this N2, that means that we are thinking of it as NC2, N choose 2. But given that, we have an adjusted rank RAND index. What we are doing again here is trying to balance our data to make sure that if there's like 10,000 different points in one cluster, 5 points in the other cluster, we don't want to overestimate based on the first cluster. So this formula here for adjusted RAND index is going to help us do that. Question, yes? Yeah. We are always thinking of this from a binary perspective, which is that given one element, is the other element part of the same cluster or a different cluster? So we are always looking at it from a binary element. That's why it's always 2 down there. Any other question? So apart from that, there's a couple of other metrics as well. Mutual information. It's very similar to entropy and Shannon information that exists, except now we are now looking not for a single data point, but rather from 2 data points together. We won't go too deep into the idea of mutual information itself. I just have one slide. But essentially, high values of mutual information is going to be better. And you're usually looking at the number of data points that exist within one cluster and another cluster in order to get your mutual information. The last one is about something called cluster purity. So cluster purity is about given a single cluster, how much of the same class is within that particular cluster. Again, now we are discussing about the fact that we have access to class labels. So now we can say that given a particular cluster, 99% belong to the same cluster while 1% is different. So that means that it's a very pure cluster compared to something like another cluster with, if I have something like this where I have all dots, but then I have like 3 x's somewhere in the middle. So that means like it's probably just 70% pure because of the fact that you have a different element within that cluster. So that is not ideal and something that we can get via cluster purity. But again, cluster purity has the issue that whenever there's imbalanced data, it's very hard to justify using something like this because sometimes anomalous data are important. So cluster purity completely underestimates that anomalous data and just uses all existing data point. So in the next couple slides, I have about a few summaries regarding k-means and GMM. Very important part is the internal metrics. Most likely they favor k-means clustering because again, whenever we discuss this, our default values, the way we use it is L2 distance. So since k-means is designed based on that, you'll have your results based on L2 distance. But external metrics, when you have access to the ground truths, that's when you'll see that GMMs are performing a lot better than k-means clustering. So the next part is about image segmentation. There's actually not much in these particular slides. The only part here which is important is that segmentation is kind of a clustering problem. We want to look at different pixels within this image and say that all these images, all these pixels belong to the same class or the same cluster, in this case a cow or a buffalo. So that is essentially why we say that image segmentation is kind of a clustering issue. The only important part here to note is that in an image, the dimensionality of my data is going to be fine. There is RGB, which is usually how we have our images, and there's an XY coordinate, which is the location of that pixel. So that's why your dimensionality is going to be fine. And I have a few examples in terms of how k-means clustering looks like, versus GMM looks like, versus like mean shift algorithm looks like. The most important takeaway from these slides is that the kind of data you're giving in is very important. RGB is probably not a good input to your clustering algorithm. Your LAB, which refers to luminosity and chromaticity, maybe is a better version. And if you remove the L, which is the luminosity, we have A and B, which are the color channels only. And these color channels give a better segmentation result than before. Look at the output here, and this is the ground truth. This almost matches these two things, right? Compare this against something like RGB, if I'd used it. It's not equal to it at all. So when you're doing your project, these are some things that you may be interested in doing. Just kind of how you pre-process your images is going to have a large impact on how your outputs are going to look like. But apart from that, I have nothing else in terms of segmentation, and this will conclude our discussions on clustering. Next week onwards, we'll move on to neural networks and deep learning.